In mesh analysis, after choosing mesh loops and constrained loops, you apply KVL and Ohm's law to write KVL in terms of the loop currents. The resulting equations are solved to determine the mesh currents, and then anything else you want to know about the circuit can be determined from those mesh currents. Before I talk about writing the equations governing mesh currents, I'll quickly review the choice of unknowns and constraints. This is the same circuit I used in the previous video. The first step in mesh analysis is to choose mesh loops. The easiest way to do this is to kill the sources. That is, replace the voltage sources with short circuits and the current sources with open circuits, and then identify any resulting enclosed but non-overlapping areas. The mesh currents go around the perimeters of these areas. If you do this, no mesh currents will pass through the current sources. The next step is to account for the current sources by defining what are called constrained loops. The constrained loops will pass through the current sources and match the magnitude and direction of the current source's currents. The only other requirement on constrained loops is that they have to end at the same node where they start. The actual path they take is arbitrary. This is a valid choice for constrained loop for this circuit. It's not the only possible choice, but it's the one I'll use for the rest of this video. Now I'll apply KVL around the mesh loops. To do KVL, we sum voltage differences, so we need to define our voltage unknowns and sign conventions. This figure shows my mesh loops, and this figure has my arbitrarily defined voltages. Remember that I can choose my voltage polarities arbitrarily. However, this choice dictates the current sign convention later when I apply Ohm's law. Now let's do KVL around loop I1. If I follow the direction of the mesh current I1, I see the negative terminal of the 10 volt source first, so minus 10 volts. I see the positive terminal of V1 plus V1, and I see the positive terminal of V3, so I'll add that. As usual, I'll add a voltage if I encounter its positive terminal first, and subtract it if I encounter its negative terminal first. Following the loop current I2, if I start here, I see the negative terminal of V1, so minus V1 plus V3 plus V4, and then I hit the negative terminal of V3 last, minus V3, those sum up to 0. Next, we'll use Ohm's law to write these voltages in terms of the loop currents. When we apply Ohm's law in mesh analysis, we have to keep two things in mind. First, the physical current going through an element is the sum of all the mesh currents going through that element. Second, we have to be consistent with the passive sign convention between our assumed mesh current directions and the assumed voltage polarities. The voltage V1 has its positive terminal here, so loop currents entering that positive node will result in a positive voltage. On the other hand, if the loop current enters the negative terminal, we're opposite to the passive sign convention, and the resulting voltage is negative. So the voltage V1 is the resistance, 1 ohm, times the sum of the mesh currents. I1 enters this positive terminal, so it's a positive contribution. I2 enters the negative terminal, that's a negative contribution. Those are the only two currents going through that element. We're done. For the voltage V2, that's equal to its resistance, which is 2 ohms, times the sum of the mesh currents. The only mesh current going through there is I2. It's entering the positive terminal, so that's a positive contribution. For V4, V4 is its resistance, 4 ohms, times the sum of the mesh currents going through this. I2 is entering the positive terminal, and the constrained 2 amp current is going into the negative terminal. I subtract that off. Finally, for V3, that's equal to 3 ohms, its resistance, times the sum of the mesh currents. I2 is entering the negative terminal, so that becomes a negative I2. I1 enters the positive terminal. I add that term on. And 2 amps, the constrained loop, enters the positive terminal. I add 2 amps. Now we can substitute the Ohm's law equations into our KVL equations from the previous slide and write the system of mesh equations. Here are the KVL equations and the Ohm's law equations we came up with previously. To write KVL in terms of the loop currents, substitute the Ohm's law equations into the KVL equations. When we do that for this equation, we get negative 10 volts plus V1. V1 is just 1 ohm times I1 minus I2. We add V3, which is plus 3 ohms times I1 minus I2 plus 2 amps. That sums up to 0. For the second equation, negative V1 is the negative of 1 ohm times I1 minus I2 plus V2. V2 is 2 ohms times I2 plus V4, so plus 4 ohms times I2 minus 2 amps. And finally, minus V3. So I subtract 3 ohms times I1 minus I2 plus 2 amps. That sums to 0. Now we have 2 equations and 2 unknowns. We can solve those for the mesh currents I1 and I2. Now let's try an alternate approach to defining voltage polarities. This time I'll choose my polarities so that they follow the passive sign convention relative to whichever mesh loop I'm following. This may result in changing the voltage polarities of some of my resistors between loops, but since my sign convention is arbitrary, that's okay, as long as I'm consistent with my voltage polarities, current directions, and Ohm's law. With this approach, when I do KVL around loop I1, I choose my voltage polarities as shown. In this sign convention, the mesh current I1, which is the one I'm following, always enters the positive voltage terminal. If I start down here, this results in a negative 10 volts. The positive terminal of this voltage is seen first, so I add that. Its resistance is 1 ohm. I1 enters the positive terminal, and I2 enters the negative terminal. For the 3 ohm resistor, I still see the positive terminal first. That becomes plus 3 ohms. I1's entering the positive terminal, so it's positive. I2 enters the negative terminal, it's negative. And the 2 amp constrained loop enters the positive terminal, so that becomes plus 2 amps. That brings us back to our starting point, so that sums up to 0. When I do KVL around loop I2, I now set my voltage polarities so that the current I2 always enters the positive voltage terminal again. Now, if I start here and do KVL, I see a positive term first. Its resistance is 1 ohm. I2 enters the positive terminal, and I1 enters the negative terminal. For this resistor, it's 2 ohms. I see the positive terminal first, so I add that. The only mesh current going through there is I2. It enters the positive terminal, so it's a positive contribution. For the 4 ohm resistor, I see the positive first, so plus 4 ohms times I2. And the constrained loop is going the opposite direction, so I have a negative 2 amp contribution. Finally, for the 3 ohm resistor, I2 enters the positive terminal, I1 enters the negative terminal, and the 2 amp constrained current enters the negative terminal, so I subtract that. That brings me back to my starting point, so those sum to 0. Now let's compare these results with my previous results. Negative 10 volts is the same as negative 10 volts. This term is the same as this term, and this term is the same as this term. These two equations are identical. For this loop I2, 1 ohm times I2 minus I1 is the same as the negative of 1 ohm times I1 minus I2. If I distribute this negative in, that makes a positive I2 and a negative I1. This term and this term are the same. This term is the same as this one if I distribute that negative in again. And finally, this term is the same. The equations turn out the same as long as I'm consistent. A shortcut for writing the mesh equations is to assume voltage polarities such that the mesh loop you're following always enters the positive voltage terminal. Then just redefine your voltage polarities as necessary for each mesh loop. This also makes it easy to combine KVL and Ohm's law to write KVL directly in terms of the mesh and constrained currents. As with nodal analysis, there's a pattern in the mesh equations that allows us to partially check the equations to make sure they make sense. When we did KVL around loop I1, we got this equation. If I rearrange the equation to group the I1 and I2 terms and move any constant terms to the right-hand side, the equation looks like this. So for the I1 mesh loop, the terms multiplying I1 are the sum of the resistances through which I1 passes. The terms multiplying I2 will be the negative of the sum of the resistances shared by I1 and I2. As with nodal analysis, this check doesn't tell us anything about whether the constant terms are correct or not. Likewise, in the equation for loop I2, the terms multiplying I2 are the sum of the resistances through which I2 passes. The terms multiplying I1 are the negative of the resistances through which both I1 and I2 pass. After we've written the mesh equations, the next step is to solve the equations to determine the mesh currents. Then we use the mesh currents to determine any parameters that we want to know about the circuit. For this example, I'm going to determine the current Ix and the voltage Vy. The current Ix is the current through the 1 ohm resistor, assumed positive in the direction shown. The current in any element is the algebraic sum of the loop currents passing through the element. So Ix is the sum of I1 and I2. The I1 term should be negative since it's in the opposite direction to Ix. The I2 term is positive since Ix and I2 are in the same direction in this resistor. So Ix is equal to I2 minus I1. The voltage Vy by Ohm's law is the resistance, 3 ohms, times the current through the resistor, with this being in the positive direction. The current is then I2 minus I1 minus 2 amps. So my voltage Vy is equal to 3 ohms times I2 minus I1 minus 2 amps. For this circuit, we want to use mesh analysis to write equations from which we can determine the current I. First, I choose mesh and constrained loops. If this voltage source is replaced with a short circuit and the current source with an open circuit, these two sections are enclosed and the two mesh currents go around those areas. The current source is accounted for by a constrained loop. I'll have the constrained loop go around this. So my mesh and constrained loops look like this. Keep in mind that the constrained loop choice is arbitrary. That could go anywhere in this circuit as long as it gets back to its starting point. If I start here and do loop I1, I see a negative 4 volts, plus, I'm always going to assign my voltage polarities such that the positive terminal is the one that the mesh current enters, plus 2 ohms times I1 plus 5 ohms times I1, and now I2 is entering my assumed negative terminal. That brings me back to my starting point, so those sum to 0. For loop 2, I2, if I start here, is 5 ohms. Now I'm switching my sign convention so that this is the assumed positive terminal. So that becomes I2 minus I1 plus 3 ohms times I2 plus 6 ohms times I2, and the 1 amp constrained loop also enters the positive terminal, so I add 1 amp. Finally, the current I is going to be I1, it's going in the same direction as I, minus I2, which is going in the opposite direction of I. There are 3 equations and 3 unknowns. I can solve those for the current I. In mesh analysis, it is possible to write the mesh equations without defining constraint loops. In the next video, I'll show you how to avoid them if you want.